Okay, well, I've had a couple of people come by and ask about the homework, and so what I did is I put you off and said, well, let's just capture all these questions on the video in case, because probably if you have questions, other people will have the same kind of questions. So your homework assignment for tonight is to rewrite sift down with a loop instead of recursively, right? So, questions?
Why?
Why? That's a good question. The reason is because iteration, as a rule, is more efficient than recursion. Because when you call a function recursively, when you call a method recursively, then every time you do a function call, you have to allocate storage on the runtime stack. And so it's the numero uno reason is efficiency. Plus, it's a good exercise for you. So that actually is a good question. And here's what we're going to do. I have alluded to this several times previously, but you're going to write a paper that takes sort data. And so we want to have this algorithm, the sift down algorithm, be as efficient as possible, so that when we take the data, we'll have data on a more efficient method than if it were called recursively. So anyway, that is a good question, actually. Plus, I mean, it really makes a good exercise for you guys, you know. Anyway, yeah.
With the sift up, are we supposed to use that?
Oh, that's a good question. You notice that there is a sift up. No, sift up does not need to be written. The only thing you have to write is sift down. Sift up is used as one of the methods in the priority queue. I think we mentioned the other day that the heaps are also used not only for sorting, but they are also used in a data structure called a priority queue. And the sift up method is for that one. And I don't even think we're going to have time to do the priority queue. We might demo it a little bit, but there's no need to do sift up, just sift down. So it can stay uncompleted. And the heap sort will never call sift up. So you don't need to worry about that. Yeah, that's a good question. Now actually, let's go back to, okay, let's go back here to figure 4.24. So the question is, I gave a little guidance in the homework assignment for this variable called done that I recommend you use. So let's take a look at figure 4.24 and see and review exactly what sift down does. So you see in part A of the figure, what happens is we are sifting down starting at 30. So I would be the index of where that 30 is, right? And the thing is that if we look at the code for this, if we look at the code for sift down here in figure 4.22, we see that it does these tests, and then the very last thing it does is it calls sift down, so it calls itself recursively. But the effect of it going down is, if we look at part A, the 30 is compared with the 90 and the 80, and the 90 is bigger, so in part B, the 30 goes down, and the 90 goes up. And then we compare the 30 with the 45 and the 55, and the 55 goes up and the 30 goes down, and then we compare the 30 with the 20 and the 40 goes up and the 30 goes down. So each one of those, each time it goes down, it's calling itself recursively. But we don't want to use recursion. So therefore, we're going to do this in a loop. So each time you go through the loop, it's going to go down, each execution of the loop. Are you with me? Now here's what done. I recommend you have a Boolean variable called done. And what it should do is it should be a flag that tells you when to terminate the loop. Because there's two different ways that the loop can terminate. The loop could either terminate by going all the way down, as it did in this sequence, all the way down to the bottom so that there is no child, or it could stop in the middle. Are you with me? So the question is, how do you know what's going to control the termination of the loop? Because it can be controlled by two different things. It can stop in two different ways. Do you see? So how are you going to, the question is, how do you make a loop that can end either in one circumstance or in another? And a common way to do this is to have a flag. And a flag, this is called a flag, and it's a Boolean variable called done. And what I recommend you do is you use a while loop, because now what's the difference between a while and a do? If you say do, where's the test for a do loop? It's at the bottom. So if you say do, that means that you're guaranteed to go through the loop at least one time. But you might be done right at the beginning. You see, so the test has to be at the top. So what I recommend you do is you have a variable called done, and the loop should be while and then not done.
Okay.
Like this. And then and now the question is, what controls the value of done? Well, you initialize done. Done has to be initialized before you do this test, because, are you with me? So done has to be initialized before you do the test. And as you're going down here, you'll have some if statements, and inside one of those if statements, if you detect a situation where you're done, you would set done to true, and then when you get out of the loop, that would terminate the loop. So this is a common use of a flag in a situation where you want to exit a loop under more than just one circumstance. You don't know how many times ahead of time you're going to go through the loop, because it'll depend on the data. Yeah. Oh yeah, that is a good question. Now, and this is a common one, and now here's what I bet it is. If you get a type here's the situation. Do you remember whenever we did sort int, what we were doing is we were sorting integers, right? But now with this sort comp assign, what are we sorting? We're sorting doubles. Now here's something to check. If you ever have like a variable inside your code and you said int temp, you had a temporary variable and you said int, it might be that you have a temporary variable called int that should be type T. And the thing of it is if it's int, it will work for the sort int project. But now will no longer work for the sort double for the sort comp assign double, because T is double. It has to be double. So do you understand what the deal is?
Yeah, so you have to go back and redefine it.
What happened was that the unit this gets back to your question. If it passes the unit test, is it correct? Oh, it passed the unit test, but it wasn't correct because we didn't test it with you see what I'm saying? Yeah, common mistake. And that's one reason we did it with sort int, and now we're sorting doubles, because the temp needs to be type T and not in general. So that's a good lesson. Yeah.
Why would you ever stop the loop in the middle? How do you know for sure?
Good question. Why would you stop the loop in the middle? Let's suppose in figure 4.24a that instead of having let's suppose that instead of moving the 30 down, we were moving, let's suppose that the 30, instead of being 30, let's suppose that the 30 is 60. Do you see what would happen? So let's just imagine that in figure 4.24a, instead of the node having 30 in it, suppose it has 60 in it. Well, what would happen? The 60, we would compare the 90 and the 80 and the 60, and what would happen? This would switch with the 90. But then we would compare the what? The 60 with the 45 and the 55, and we're good. So that's a scenario in which it would stop before it gets all the way to the bottom. Yeah. You know that if it stops there, that the left child and the right child of the node where it stops is. That was a good observation. You know that the left child and the right child of the node where it stops, they are already max heaps. So it can stop there and it'd be good. Oh, that was a really good observation. Yeah.
Three cases.
No, yeah, hold on. I think I know how to answer your question. Now it's going to be, let's go back to figure 4.24a again, A and B and C, and watch what happens. When we do this, here's an answer to your question about efficiency. Here's a question about, here's another aspect of your question about efficiency. Check this out. In part A, what happens is, we compare the 30 with the 90 and the 80, right? And then what happens is the 90 goes up and the 30 goes down. So what do we do? In part B, what happened? We actually switch the 90 and the 30. And then in part B, we compare the 30 with the 45 and the 55, and what do? We actually switch the 30 and the 55. And then in part D, we actually switch the 30 and the 40. That's inefficient. Now that we're doing it with a loop, we can even be more efficient than that, because what can we do? In part A, what we can do is we can say temp gets the 30. Are you with me? And then as we go down, the 55 will go where the 90 is, and the 40 will go where the 55 is, and only in the end we can put the 30 where the 40 is.
Oh, you don't have to like swap.
You don't have to swap them all the way down, because that's unnecessary assignments. Are you with me? So that yet more efficiency, see, compared to the recursive version. Is everybody clear on this? And what should be the type of temp? Double?
T.
T. Right. So you see how, so you set that all up, here before you get into the loop. What's the criterion for setting done?
It has to
Yeah, you know, in other words, when would you quit? When would you quit right off the bat? Right. If he doesn't have a child.
I suppose in this.
Well, wait. Well, the precondition for the sift down is that, I mean, it's between low and high.
Oh, okay.
I mean, you know, so it's a legitimate index.
Okay.
It is a legitimate index, and we know what low, and the parameter list, you know, has low and high in it, so we know what low and high are, and so we can do all those tests. But the logic is very similar. I mean, the logic of determining the left child and the right child and whether there's bigger, all that logic is the same. It's just that when you get to a situation where you know you have to stop, you just set done. And what you'll do is, and what will you do to terminate the loop? You will set done to true. So when you get to the loop, then boom. And then what happens? Outside the loop, you'll do what? You'll actually put it where it belongs.
So there's
Once outside the loop, so you don't swapping it all the way down. No. Oh, yeah. So this is that old thing. We're not sorting. We are not sorting. We are only doing this. We are only implementing sift down, which is used in two different places. Where is it used? To do what at the very beginning? To build the initial heap, and then it's also used where?
Sort.
To do the. And it's used where? Where else?
split.
To do the split. Oh, these are all really good questions. Now, are we all fine on this now? Now, you know, you might want to use Piazza tonight now, because there might be some, you know, I noticed that the traffic on that has not been very big. But now I think from now on, and especially the next thing we're going to do is link lists. So now we're getting to the point now where we are going to be coding a lot from now on till the end of the semester. Last time we did, we looked at this technique for, well, first of all, we looked at metrics. And we had three different metrics, which are, and what is a metric? It's a measurement. It's a way to measure something, like the same way that temperature, the same way that temperature is a measure of how hot it is. These metrics are a measure of how many statements execute, only they're just certain kinds of statements or certain parts of statements. So we have a comparison, and then we have a probe, and then we have an assignment. And the two that we're going to use, to take our data, are the comparison and the assignment. So that's comp assign, and that's the CA metric. So it compares the comparison and the assignment. All right. Now let me emphasize again. You got a question?
Is there a reason why we're picking those two and not all three? Or?
Well, it's just a matter of time. I don't. In fact, as a matter of fact, in the paper, I'm only requiring you to do the comparison and assignment, but the probe is done. I mean, the probe is set up, and if you want to install that and explore that, that might be a good idea. I mean, if you're interested, you know, and you see some things in your data that you want to kind of like verify or investigate further. So, and let me say also that, emphasize again that the parametric decoration that we're doing now is actually not one of the object-oriented design patterns because it's not based on inheritance. And so that's not in the Gamma book, but the decorator design pattern is, and that's what the probe, that's for implementing the probe metric. And you can take a look at that code. We just don't have time. You know, what are the 3 goals? We even have 3 goals. I mean, so we're trying to do so much. We're trying to do a lot in this course, and so we don't have time to do, you know, as much as I would like in each one of those 3 goals, which are. Yeah, well, the first one is data structures. The second one is object-oriented software design, and then C++. So we're learning all 3. We're learning aspects of all 3 things. But anyway, so I will remind you again that the decorator design pattern, the one that we're not using, is one of the patterns in the famous Gang of 4 book. And so let me just recap. Let's just review a few concepts. So here we have the counter in figure 4.30, and the counter has 2 things, the delta and a count. And do you remember what the delta is for? What's another word for?
How much each of the costs?
Yes, it's good. It's the cost. So and in our project, it's always going to be 1, but we have it in here in general. So in case you want to use the counter to do some probes or some whatever, and you want to have a different cost for a different counter. And then the other thing, and then we have an update and a clear. And so whenever we do update, that's when the counter is incremented. And now, what was the main idea in parametric decoration? We don't sort type double. Instead, we sort an object that has a class CA metric. And in CA metric, we set up 2 counters, one to count the number of comparisons and one to count the number of assignments. And now, let's review this because this is super important. Here in CA metrics, in figure 4.31, we have class CA metrics, and we have private, static, counter, compare count, static, counter, assign count. What is the meaning of the C++ word static?
There's only 1
Per
class.
what?
Class.
There's only 1 per class instead of what? 1 per object. So you understand that if we are sorting 100 objects, we don't want 100 different counters. We want, each time we increment, you know, each time we compare 2 different CA metric objects, we don't want to have, you know, 1 counter, you know, go up and then another counter go up. We need to increment the same counter. There has to be 1 counter for the whole class. So everybody see that. This is a crucial idea in C++. So it means 1 per object, and it means 1 per class instead of 1 per object. And you see why we need to do it that way here. Okay? And then we have underscore data, which is type T. And so each one of our objects holds the data that it needs to hold, but it also has in it these counters. All right? And then we were looking at figure 4.31 near the end of class last time. And what we have here is when we say bool operator less than, and then it has a CA matrix right-hand side, that we are overloading the less than operator. Are you with me? So what happens is when you say, if you say if A subchild is less than A subchild plus 1 or whatever, then what the compiler does is it takes a look at this less than. If this were an int and this were an int, it would generate code for an int less than. If this were a double and this were a double, it has built into it the ability to generate code for a comparison of two doubles, which are stored differently than the way two ints are stored. Are you with me? But on the other hand, if this is of type CA metric, then what does the compiler do? It goes and it looks to see if there is an overloaded operator that has type CA metric. And because there is, it will execute this less than. Yeah.
It's because they're both considered type T, correct?
Well, actually, that's a good question. A subchild is not type T. A subchild is a CA metric.
Okay.
And inside the CA metric, the underscore data inside the CA metric is type T. Well, I guess it's which T are you talking about? There's two big T's. There's a T for the there is a T for the CA metric, and then there is a T for the array.
Yeah, I was talking about the T for the array.
The T for the array is a CA metric,
Yeah. Yeah,
not a double.
yeah.
Okay, but the underscore data inside the underscore data inside a CA metric object is that T is a double.
Yeah. Yeah.
So what happens is when the compiler sees that the type of the A subchild is a CA metric, it goes to the it goes to this operator CA metric, this overloaded operator, and it executes that code. And we saw what that code does is here later on in figure 4.33. It says what it does is, oh, here's the less than operator. So first of all, what it does is underscore compare count dot update. So what does that do? Updates the counter, and then it takes the underscore data part of the left-hand side and the right-hand side dot underscore data, and it returns true or false depending on what that comparison is. So it's actually comparing the underscore data part inside each CA metric and returning it for the compiler, and then this is either true or false.
And because,
oh, you finally got it. Now you're getting it. Yeah.
Since it has to call this other operator, we're able to put in the counting method into the...
Yes.
That's cool.
Now, yeah. Oh, good. We have some aha moments.
Is there a reason that we're doing compare count dot update instead of just compare count plus plus?
Because update is one of the methods of the counter. Remember, we have one counter inside this class.
Right.
And update is a method here. Let's go back. Here, check it out. So here, in figure 4.30, we have class counter. Are you with me? And it has underscore delta and underscore count. And then later on, here's the method. It's called void update. Count plus gets delta.
Okay, I see.
Yeah. Now, yeah, I think.
Because that like...
a counter is a class.
It's an object.
Yes, it is. Yeah, yes, it has its own class. And look here. Let's go to CA. And let's look here at CA metrics. What is static counter? So there's the counter that it's executing. So it's executing the method of that counter. Yeah. No, in figure 4.31. That when it says template class T, class CA metrics, that T is going to be double.
Okay.
Because look what it says. It says T underscore data. So that's like saying double underscore data. So that's like saying the data part, the data attribute of a CA matrix is a double.
So when do you define a...
Yeah, I don't have a slide. That's a good question. And I don't have a slide for that. It's in the, what you should do is look in the main program of the sort comp
Just wanted to make sure I hadn't
assign.
missed a step in the explanation.
Yeah, that's a good point. But if you go to the code inside CA sort comp assign and look in the main program, and what it will do is it will set up the arrays to be arrays of CA metrics, and that's where the CA metric will be in. Yeah, that was a good question. Yeah, is everybody? And yeah, and I don't have a slide for it, but anyway. Oh, okay. I feel like we're getting good with this now. Yeah? Now you see, so this is now, and here's the thing, you guys, in your paper you need to describe this, because you're going to be using this software in your paper, and you need to describe for the reader what's going on, what's going on. So it's good that we're understanding this. And now let me just show you one more thing before we go on. In figure 4.31, also we have these methods: get compare count, get assign count, clear compare count, clear assign count, and set cost. And these are all can be used by the main program. But now what do we have in front? We have what? Static, right? So these are static member functions. All right, so what we do, the way we access these is not through an object, we access them through the class, because these are class methods. Yeah.
Can you draw a class hierarchy so that we can see what falls on?
There is no class. If you notice here, there is no inheritance.
Okay.
This is not an object-oriented design pattern. So there is no inheritance. So there is no class hierarchy.
Okay.
It's all class composition. See, look, if we come back here, if we come up here, we see that CA metrics has a counter, and there's no colon anywhere. See, so a CA metric, a CA metrics has a counter, and a CA metrics has an underscore data. So actually, that's consistent with the fact that the parametric. So that is consistent with the fact that this parametric declaration is actually not a design pattern, an object-oriented design pattern. But it does. So because it's based on what it's based on is we're using the C++ template facility. That's what makes it possible.
Okay.
And together with function overloading.
So do you do like an include? Like how do you access the?
No, well, you just put them in your to compile. You just put you put these classes in your include list. Yeah. Okay, is everybody good? Now, what I would like to do for the rest of the period is to talk about the paper. Now, your paper is going to be due in 2 stages. The first stage is going to be due on Tuesday, but it's just getting stuff set up. There's not a whole lot of writing to do. And then I think it's not until assignment 14 or something like that the final paper is due. So I'm giving you lots of time. In fact, it's even going to be after we take the next exam. But I'm giving you all this time because you'll probably need it, and so you shouldn't wait until the last minute, to get the paper done. So what I'd like to do now is talk about the content of the paper. Okay, so let me just say at the outset here that I want you to use 2 tools, and these tools are really going to serve you well if you continue on in computing or any scientific discipline. The first tool we're going to use is R, with RStudio. It's a programming language that's statistics based. And the second tool we're going to use to do the actual typesetting is LaTeX, which is the TeX. Now, I know you guys in physics probably already know how to use LaTeX. But let me just say a word about these tools. Both of these tools are very widespread, and they not only are they widespread, as the years go by, they get more and more entrenched. They are both open source tools. They are both very solid, well-known, widely used tools, and any science person, even regardless of your majoring or minoring in computer science, all science, many of the sciences use both of these tools. In fact, some of you, we even have any of you guys, did any of you guys take the 105, the R-based? Oh, good. So a few of you are already familiar with R. So you have a head start with the rest of us. Okay, so we have one of the sections of the intro course now is done in R. So what we want to do is what you'll have to do is you'll have to analyze your data using R with RStudio and then write your paper using LaTeX. So LaTeX was invented by Donald Knuth at Stanford University many years ago, and it has stood the test of time, and it is an amazing open source typesetting program that is widely used. So anyway, I have three documents for you. One called Setup for RStudio, one called Plotting Raw Data in RStudio, and another one called Curve Fitting in RStudio that describes how RStudio works. And then I have another set of documents that describe how LaTeX works. What I want to do today is finish up today is to show you how to analyze your data in RStudio. Now, on this next slide, this is a screenshot from the document. It's the document Setup for RStudio. What it is it's a command line tool, and here's a screenshot of what RStudio looks like, and in the lower left-hand corner there is a console, that you use. It's a command line console, and I've got resources for you to look at for how to use the console. We don't have time to learn it all here in class or go over it in class, but I have some resources for you to pick out. It's very simple, and then on the upper right-hand part of this screenshot, there are these functions. I have written some functions for you. So I'm not requiring you to know how to program, to learn how to program in RStudio, because I have some pre-written scripts for you to use, and the documentation shows you how to use those scripts. One's called dp4ds fit, another one's called dp4ds raw plot, and is all you need to do is there's guidance in the documentation for how to use those. So anyway, that's the basic setup of RStudio. You actually have to download two things. You have to install two things. You have to install the R language itself, and then after you install the R language, then you install RStudio, which uses, it's a separate project. It's a separate organization, RStudio, that presumes that you already have R installed on your computer. So you do them in that order. Install R, the R programming language, and then RStudio. And on this next slide here, I have an example of plotting, how to plot raw data in RStudio. So what you're going to do, what you'll do is you'll use the sort comp assign to take the performance data. And here's a little command line argument. It looks very long, but there's a nice history feature in RStudio, and you only have to type this out once, and then so it says, see here it's executing this dp4ds raw plot, which is a script I wrote for you to use. And then if you type this out and you have your data in these, if you set up your data accordingly, then it'll print out this plot, and it'll put the legend on the side and put the legend, you put what you want to be on the legend. Notice that on the bottom here it says number sorted, and that's the first, you can see number sorted in the arguments for the script, and etc. Okay? So all those details, I've written that script for you to use, and when you want to plot the raw data, you just follow the recipe and put what you want to plot, however you want to plot it. All right? So that's an example of plotting raw data in RStudio. Now, here comes a big idea. Do you remember what we've done is we have 5 different sort algorithms, and we know what the theoretical performance of asymptotic performance of each one is, right? They are either what? Each one of those is either what or what? It's either quadratic or it's n log n. Are you with me? And the question is, if you take data, how can you tell by looking at the data whether this data is quadratic or the data is n log n? Well, we know theoretically what each one should be, but we don't know what the data is. We don't know if that's consistent with the data. Are you with me? That's the question. The question is, if you plot, if you plot the number of comparisons as n goes up and it curves up like this, is that curve an n log n curve, or is that curve a quadratic curve? You see? Does everybody understand what the question is, what the problem is? That's the problem. And there is a statistical tool that we can use to run a test to determine which one it is. Okay, so the question is a plot a performance metric versus n, t of n equals big theta of n squared, or is it t of n equals big theta of n log n? Now here's the answer. The answer is in this quantity called the residual standard error, which is RSE. Yeah? And what we want to do now is we want to understand what the RSE is. Mathematically, it is the square root of the sum of the y sub I minus the y hat sub I squared divided by d dot f, which means degrees of freedom. Now that sounds like a mouthful, but it's not too bad. What we're going to do is we're going to go through now and see what each one of these things is. All right? And the way we're going to do it is we're going to do a simple example with a line. So, what's the equation for a line? Y equals ax plus b. A is the slope, b is the y-intercept. Are you with me? Okay? So that's what. So here's what RStudio, what R will do for us. What it is able to do? It is able to adjust A and B to minimize the RSE. So let's take a look as an example. So on this next slide, I have a picture of some data. So those red dots represent data. Are you with me? Those red dots represent data. So, and you can see, when x is real small, y is real small, and they kind of like go up, but there's some scatter in the data. All right, and there's actually one on the y-axis there. So there's those are the little red dots. So there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Right? And now you see this green line here? This green line is plotted with a particular slope and with a particular intercept. Are you with me? And for this slope and this intercept, what happens is, now you see I've taken that one data point in the middle, and you see the y hat sub I is the y value on the line, whereas the y sub I is the y value of the data. Is everybody clear on that? Yes.
How did we come up with this line?
That's a good question. How did we come up with this line? Let's think about that. Now obviously, yeah, let me hold that thought.
Okay.
Here, before I answer that question, let's talk about let's take care of this little degrees of freedom in the denominator. This d dot f is degrees of freedom. That's the number of data points minus the number of coefficients. So in this particular example, let's count the data points. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. There's like 15 data points. And how many coefficients do we have? A and B, there's 2. How many data points did I say?
15.
So 15 minus 2 is 13. So the degrees of freedom now is 13. So now, so what is this? Let's go back to what is this sum? Y sub I minus y hat sub I squared divided by degrees of freedom. It's the square root of, now you take every y sub I minus y hat sub I, you square it. Take the next one, you square it. Take the next one, you square it. You take the next one, you square it. You take the next one, you square it, you square it. Take all those squares and do what? Add them all up, divide by 13, take the square root of that, that's the RSE. Now can you imagine going back to this figure, what would happen if instead of this green line being here, suppose the intercept, the B, was big. What would happen if the intercept was big and then you calculated the RSE?
It'd be bigger.
It'd be bigger because all those differences between the data and the line would be bigger. Are you with me? And you square them, so whether it's positive, the positives and negatives don't cancel out because the minus and minus is, if you square a negative number, it's positive. All right? And also can you see, so do you see that what the program is able to do is it's able to adjust. Can you also see that if the slope were different, suppose it was right here, but instead of being tilted this way, it was going whoosh, it was like this. So what would happen to the RSE?
Go up.
The RSE would go up because those deltas would be bigger. It's able to calculate the A and the B to minimize the RSE. That's where that green line came from. Are you with me? Does everybody see what? There's a mathematical way to do that.
So it does that.
Yes. It, in fact, and the RSE is, the A and the B are adjusted to make the RSE as small as possible. It literally minimizes the RSE. It does that. So that's why the line looks like it's going right through the middle of all the data points. Do you see? Because if it didn't go through if it was like shifted up, you know, there would be an A and a B that would make the RSE smaller. So that's the slope and the intercept to make those sums of all those squares divided by the degrees of freedom square root the smallest possible. Does everybody see that? Does everybody understand how that works? All right. So that's why we say, so we adjust A and B to minimize the RSE. All right?
But this is a function, a feature of R.
This is a feature. R can do this for us automatically. We don't have to pull out our calculators and do all that stuff. And it's built in. All right? So what you do for a line, you adjust A and B in y equals ax plus b to minimize the RSE, the residual square error. Residual standard error, sorry, to the residual standard error. Okay, but now look, our data is not in a line, our data is going to curve up. Are you with me? So instead of having ax plus b, what do we have? Well, we could have what? an squared plus bn plus c, or we might have what? an log n plus bn plus c. Do you see what I mean? That's the shape. We want to know which curve is it. Do you see what we're saying? So what can the software do? It can, instead of adjusting A and B, it can do what? It can adjust what? Just A, instead of just adjusting A and B, it can adjust what? A and B and C to do what? To get it to fit as good as possible. But now look, do you see then that what we should do is, if the data is more quadratic, then what will its RSE be? Lower. Now that is the key idea. So this is a number. We can the statistics can calculate a number that we can then compare. We can calculate a number assuming that it's this kind of a curve. Calculate that same RSE number assuming that it's this kind of a curve, and then we can compare those two numbers to determine which is the better fit, and therefore which, and then see, and then hopefully that matches the what?
Theta.
That matches the theory. See? We are comparing experiment with theory. Now, is that cool? Yeah.
For the quicksort, we're obviously going to have to do the quicksort a lot of different times and take the average.
Yeah, that's a good point. That's a good point. There's some, I've noticed, in fact, the quicksort is a little problematic, is going to be a little problematic with this.
Yeah, because it gives you a
Yeah, that's a good point. Yeah, so you're going to have to grapple with that. This is typical research type problems that we have to grapple with. Yeah.
Is it really going to be that bad if we're doing like so?
Well, we'll have to see. You'll have to see. We're doing an experiment. Who knows? You see what I'm saying? But that's something to think about. Yeah, all these are issues that you're going to think about, to grapple with. Okay? All right, good deal. So we'll continue this on Monday.